Okay, let's get started. So, any question from this time? If not, okay, so a quick review of this time. So, last time we finished talking about the properties of discrete time Fourier transform. And so, as usual, we have those tables that can serve as a reminder. So, those are all the properties of discrete time Fourier transform that we've gone through. So, obviously, we have linearity and have a time shift. Then you get this h equal minus j omega naught. And if you have a frequency shift, then you get this h equal j omega naught. And conjugation, as usual, you get the h conjugation and the minus sign on your omega. And time reversal give you frequency reversal. Then time expansion is something weird because you need to make sure you are still taking your integer values. So time intervention kind of not working, and the only case we make it work is we define this weird x sub k function, which is you expand all your x of n by a factor of k, and in the middle you just fill up with a whole bunch of zero. And so that's kind of like you taking x of n minus n divided by k. And the result is you divide n by k, then you multiply omega by k. Okay. And the convolution is as usual, you have convolution in the time domain, then you have multiplication in the frequency domain, and you have multiplication in the frequency domain. Sorry, you have multiplication in the time domain, then you also have convolution in the frequency domain. But convolution in the frequency domain is a little weird because it's periodic, so you need to do this periodic convolution. And then you have a difference, which is basically just linearity and time shift. So you get h e to 1 minus e to the minus j omega. Then accumulation is like a inverse of difference, so you get this 1 over 1 minus e to the minus j omega is the inverse of this, but there is also a delta function term. It is pi times x of omega equals 0, then this delta function is 0 and 2 pi k. And so that's a difference in the accumulation in the time domain. And difference in the frequency domain is, then the frequency domain is continuous. So you can take a differentiation, then as usual you take a differentiation, and you get a minus j omega, minus jn on your time domain. But you can put the minus j to plus j on the frequency side. And somehow we don't think about the integral of this, but you can kind of guess. You take an integral, and something funny happen here also. And you take integral, and you get a 1 over n, but it's discrete time, so so the zero term you need to deal with the other way. Mostly is that if you do integral, then the integral won't quite converge like in the continuous Fourier series. The integral will be mostly undefined. So anyway, we don't have integral here, so let's ignore that for now. And then we have those conjugation symmetries for real signal. So for real signal, as usual, you will have big X equal to big X star with minus omega. Then you can look at this big X in the Cartesian coordinate and the polar coordinate. Then you analyze this equation in Cartesian coordinates. It tells you that the big X, the real part of big X is real, and the imaginary part is odd. And also, if you take the amplitude should be even, and the angle should be angle should be odd. Then you can combine the real even and real odd as usual, and it will tell you the big X is real even or imaginary odd, etc. And all those are the real odd things. And finally, we have the possible relationship as usual. We have the energy in the time domain equal to the energy in the frequency domain. But there is usually weird normalization. Now the normalization here is you need to divide by 2 pi. So it's average energy in one period in the frequency domain because it's periodic in frequency domain. And in the time domain, there is no period, so you are just taking an average of minus infinity to plus infinity. Okay. And we have another table that are the good Fourier transform pairs that you would like to remember. So first is that if you have a periodic signal, then the Fourier transform are going to be sum of impulse trends. So if you have a coefficient ak here, then you will get the same coefficient ak with delta at omega 2 pi k over n. And the k will be from minus infinity to plus infinity because you need to repeat itself for every 2 pi. Also, there is an extra 2 pi in front. Okay. And so that's what happens if you have a periodic signal, and then you can look at the individual component. So you have this exponential e to the j omega n, then you will get 2 pi times the delta function and omega equal to omega naught, and repeat itself at every 2 pi. So you get extra 2 pi L. And then there is sine and cosine. Sine can be looked at, cosine can be looked at as like e to the cosine can be broken into e to the j omega plus e to the minus j omega naught. So you have this plus omega naught and minus omega naught here. Then sine can be broken into e to the j omega naught minus e to the minus j omega naught. Then so you have this plus omega naught and this minus omega naught. And then you have a constant function, and constant function is omega naught equal to 0. So you put in here with omega naught 0, you get this delta of omega minus 2 pi L. And then you have something more interesting. You have a periodic square function, square wave. This between minus n1 to n1 is 1 and otherwise it's 0. Then you have this sine over sine thing. You have this ak equal to sine over sine, and the peak value is still at 2 pi k over n. And finally we have this impulse trend, then it's still impulse trend. And for the non-periodic function, basically the thing we know is this exponential decay up to the n un, and then it's 1 over 1 minus alpha e to the minus j omega, and then you can take like a family of those. So it's 1 over 1 minus alpha, then it's alpha or a? Okay, it's actually a here, but anyway. And then you can think about what happens if you have multiple power of those. So say you have this 1 over 1 minus a squared, then what happens is you get extra n to a extra polynomial term in front. So here is n plus 1 when it's squared here. Then if it's okay, so it's really small, you see. Okay, so if we have r's power here, then we have the formula. And it's n plus r minus 1 factorial over n factorial r minus 1 factorial. So I guess it's not quite polynomial, it's a rational function of n here. Oh, yeah. Yeah. It's a weird rational function of n. And anyway, you can derive this by doing by using the differentiation formula. But it's more complicated than the continuous sine case because it's e to the minus j omega thing. Then you will get extra e to the minus j omega. So it's quite complicated. You can see a higher power, but we have the formula here. And for other thing, we still have our square wave function. So the square wave function in the time domain, now it's not periodic. Then you no longer have delta function, but you still have the sine over sine structure. And Now you have the sinc function in the time domain, and you have square function in the frequency domain. And delta function give you 1 as usual. And the unit cell function give you this thing very weird that you can derive from integration, the accumulation. And finally, you have a delta function with a shift, then you get e to the minus j omega the naught. Okay. So that's a review of what we talked about in this chapter. Any question? So those are basically all the property of discrete time Fourier transform. And then today we are just going to finish this chapter with duality and how to solve difference equation. Okay, so duality. Review of duality. So we have duality in chapter 4, and it intuitively is this picture. So it says if we have something in time domain transform to something in the frequency domain, then we can kind of swap them around with a little scaling and maybe some flip around. But basically, if you put this frequency domain signal to time domain, then you will get this time domain signal to the frequency domain. So there are little scaling things. So the actual equation are here. So you have small x of t equal to big X of j omega. Then if instead you write big X of jt, so pull this to the time domain, then the corresponding thing will look a lot like this x of t, but actually 2 pi times the x of minus omega. So you need to put this t to minus omega and you need to times 2 pi. But it will look very similar. Okay? So that's duality in the continuous time. But now we think about what's duality in the discrete time Fourier transform. And we look at these two signals and look at those two equations and we think there is probably no duality between them because one of them is a continuous time periodic function and another is a discrete time a periodic function. They just look very different. So how do we get the duality? And we kind of already spoiled this. So we think about, so by itself, this discrete Fourier transform has no duality. But actually you will have a duality to the continuous time Fourier series. And so, but that's a little far away. We're doing this in kind of funny order. So we're going to talk about another duality first. So actually there is something that has duality with itself. It's the discrete time Fourier series. Okay. So that's what we talk about in chapter 3. So if you look at the discrete Fourier series, you see that in time domain it's a discrete function with discrete time function that's periodic. And in the frequency domain, it's also a discrete time function if you think it is ak as a function of k. And it's also periodic. So those two are actually very symmetric. So in a discrete time Fourier series, this x of n and a of k are dual to each other. And so that's the first thing we'll talk about. And there's another duality that's actually between the continuous time Fourier series and the discrete time Fourier transform. Because this x of n is like this a of k is discrete periodic function, and this is also discrete periodic function. And this big X is continuous time periodic function. This x of t is also a continuous periodic function. You remember? So that's what we go do in 5.7.2. Okay. So let's first look at the duality in discrete time Fourier series. Okay. So this thing. So yeah, as we say, we have those AK that are Fourier series coefficient, and so what we saw before AK are those coefficients before this exponential. But anyway, we write it a sub k because well, it's a function of k. So for different harmonic number, you have a different AK. But we can, so we write it a sub k, but obviously we can just rewrite this as a of k. And we can think this as a function of k, right? So this is basically just changing notation. Okay. And But if you remember what we talked about in chapter 3, so in the discrete case, because the frequency are always periodic, right? So as we say always in every discrete case, the frequency function is also periodic with a period with like in 2 pi frequency, right? And when that translates into k, that means that ak is periodic in k, and actually that means ak is periodic with period big N, just like the period big N for x of n. Okay, so we prove that. If you don't remember, you can check that. And and also if you look at those two equations, you see they are very similar. So ak is the summation x of n times complex exponential with minus sign, and also 1 try 1 over n. And x of n is summation ak with this also complex exponential but with plus sign. So you see like those two things are very similar, except you have h minus sign here and h 1 over n here. And so you can move it around and get a similar thing. We get similar duality like in chapter 4. So let's suppose we have some g of n and its Fourier series coefficients are f of k. So they form this pair. Okay? And so by the equation here, so we have it here. So we have the ak. This is the analysis equation. So ak should be 1 over n some x over n minus jk omega naught n. And so the ak is this fk. So obviously we have fk equal to 1 over n, then sum over 1 period, and this. Now xn is g of n, and you have this minus the exponential. And just as we said, then we want to make this equation look like this equation. Okay, so obviously we want to swap n and k now. So instead of f of k, we want to see what happens if we treat f of k like f of n. So we swap k to n and n to k, but also extra minus sign to make this extra minus sign disappear. So we just do change of variable, then you see fk become fn, and obviously 1 over n thing is still here, and some minus k from in 1 period, and g of n become g of minus k, and this kn also become, so minus kn become plus kn because you extra minus sign here. And then basically we are done. Then we just move this 1 over inside because we can, and then this minus sign on k doesn't do anything, because if you think about you are summing minus k in 1 period, you are also summing plus k in 1 period, because this is like summing from minus k from 0, 1, 2, 3 to n minus 1, and then plus k you are summing from 0, minus 1, minus 2 to minus n plus 1, and that's also summing over 1 period. So those two summations are actually the same, and so you write things in here, and you compare this to to this equation, so to your synthesis equation. Then you see that if your x of n is this f of n, then ak will corresponding to those two terms together. So ak will be this 1 over n g of minus k. So we derive that with just this change of variable and the grouping terms. We derive that f of n will have a Fourier series coefficient 1 over n g of minus k. And in summary is this. So if g of n is a Fourier series coefficient, has Fourier series coefficient f of k, then you put this f of k into a time domain, so you have f of n here. Then its Fourier series coefficient will look a lot like g of n, but you have this 1 over and minus sign on your frequency. Okay. Question about the derivation? Not there. Maybe let's see an example. And so I think, okay, maybe we didn't. But okay, so just like in continuous time, so we have this square function to sine over sine duality. So if your time domain function is this square wave function, so it's 1 between 0 and 2. So maybe it's h a little. So 1 between -2 and 2, and then it has this period 9, so excuse me. And then it has this period 9, so it's 0 between so it, maybe it's, let's draw this. Okay, so wait, oh. Yeah, and one period is between -4 to 4, so it is square wave thing. Okay, so square wave, so between 0 and 2, and it's 0 and 0, 0 and 0, and then you will repeat itself, so 0, 0, then it's square wave, etc. So the square wave thing, and then in a frequency domain, it will kind of look like sync, but not quite, because it's sine over sine needs to be periodic with period 9, and okay, it's actually very hard to draw. So maybe something like this. Okay, it's 5 period, so it's very hard to draw. But it's kind of like this thing. And it's also discrete. And anyway, just like the continuous case, now if you pull this sine over sine thing to the time domain, then you will get a similar square wave function in the frequency domain. And but you need to recycle below thing, but you need to change things a little bit, so you need to divide by this 1 over 9. And also you need to get basically a frequency reversal, so you get the minus sign. But we start with the even function, so that doesn't do anything. So you just have the square wave function with 1 over 9. Okay. So yeah, so that's a duality in discrete Fourier series. So whatever you have a time domain to frequency domain, you can swap them around and put the square frequency domain signal to time domain, and the time domain signal will be similar to in the frequency domain. Okay. And then just like before, from this we also have like a duality in the properties. So say you have this time shift, you get minus exponential in frequency, and frequency shift you get the plus exponential in time domain, and also you have the convolution in time give you multiplication in frequency. That also says you have the multiplication in time give you convolution in frequency, etc. Okay. And no question, and let's go to the next duality. Okay, so we say we'll have this funding duality between continuous time Fourier series and discrete time Fourier transform. Okay, so how does that work? So let's list all the equation here. So continuous time Fourier series, it says we have a continuous time periodic function, and it can be written as the sum of harmonic complex exponential with coefficient ak. And then we have our discrete Fourier transform says that discrete Fourier transform says that we have discrete time periodic function, and it can be written as, well, this integration of different of the spectrum with e to the j omega n. So it's also kind of like the it's also kind of like a linear combination of this complex exponential, but the frequency is continuous time is continuous, and its big X is periodic. And so maybe it's easier to, maybe I should compare this. And so when we write this discrete Fourier transform, and we write the inverse Fourier transform equation, then we look at this big X over j omega, then we find out that it is a continuous frequency function, but it's periodic with period 2 pi. So this big X is kind of like this small x of t in that they are both continuous, and they are both period, and they are both periodic. But the small x is periodic with whatever period big T, and this is periodic always with a period 2 pi. Okay. And so if we want to make those things together, so what we want to do here is transform those two equations to the bottom two equation. And you want to transform this equation to this equation, and this equation to this equation. You see how they are both very similar. So the small x should become this big X, and t should go to omega, and omega should go to t, and a should become small x. Okay, and so the first thing we notice here is that the upper thing it has whatever t, so t can be whatever positive number, but down here the t is always 2 pi. Because this discrete also always have integer value, and give you this big X also periodic in 2 pi. So the first thing we do is we do time scaling for the continuous time Fourier series. And remember what happened in time scaling? Time scaling is one of the weirder property we had. So time scaling actually doesn't change the Fourier coefficient. So what happens if you do time scaling in the in a continuous time Fourier series is that you change, so you scale time to alpha t, and then the alpha k, so you change x of t to x of alpha t, then your ak doesn't change at all. So the only change is that your t will change to t over alpha. Okay. And so that's very good. That's what we want to do. So we want to change our big T to 2 pi. So what we do is we pick alpha equal to 1 over omega naught. Then your T goes to T divided by omega naught, and so small t goes to small t divided by omega naught, and big T goes to big T times omega naught equal to 2 pi, and that's also change omega naught to 1. Okay. So first you do this thing to scale your big T to 2 pi, and then you do a change that just like before, so you change T to omega and K to n, but you want a minus sign somewhere, so you have K to minus n, and then finally you say this, now this AK become A over minus n, and you just change that AK to X over n, and this x over t become x over omega, you change it to big X of j omega, and so if you do all those three things in sequence, then you will change this equation to this equation, and this equation to this equation. So let's check a little. So this a sub k will become a sub minus n, and we say a sub minus n is x over n, and this 1 over t, t is 2 pi, so this become 1 over 2 pi, and t become 2 pi. And x sub t is t become omega, and x of omega is big X of j omega, and this is e to the jk omega naught n. So omega naught is 1, and jk t, so kt become minus omega n. So the minus sign disappears, so it's e to the j omega n, and dt is d omega. So you see that we have changed this equation to this equation, and similarly you can check out this equation will become this equation with these substitutions. Okay, and yeah, so that's basically the duality. And obviously, if you want to go other way around, then you can reverse those, etc. And so maybe let's see the example. And okay, so this is one of our favorite continuous time Fourier series. So it is square wave function. Okay. But it's periodic, so it's a square function with a width 2t1 and a period 2 pi. So we check the period is already 2 pi, so we don't need to do the scaling here, so that's easier. So if you have a period 2 pi in your time domain, and as we said, it's our favorite thing, and it has those ak that's sinc function, so sin k over k, although it's discrete time, so we are sampling the sinc function in the discrete values. And as we said, then we pull this ak to the time domain. So now we think about the sinc function in time domain, and we do discrete Fourier transform. Then we find out that the Fourier transform is our will be our square wave function. Okay. And yeah. There is no other scaling, so it's basically just the only change here, so we don't need to do this, and here we're only swapping tk to omega n, and the minus sign here doesn't do anything because both of those are even function. Okay. Yeah. Yeah, so you see that you can swap those around, so you have a square function Fourier with Fourier series coefficient being sinc. Then you can think about sinc function in time, and the spectrum will be the square function, and with period 2 pi. So this is a little easier example because the period is already 2 pi, so it works through. Okay, question about the duality. So okay, so maybe I can talk a little bit here, and so yeah, so from this duality, then you see that the discrete time Fourier transform and the convergence is a bit funny. So we talked about this a little before. So we have said that there is no Gibbs phenomena if you have a square function in the time domain here, because it cannot discrete and don't see the Gibbs phenomena wiggle. But from this duality, then you remember this square function, it has Gibbs phenomena, right? So if you try to converge into this square wave function with this sinc function, and you are taking like some finite number of terms from this sinc function and try to converge back to this square wave function, you will get Gibbs phenomena. So the same thing should happen here. So you have a square function in this spectrum for your discrete time Fourier transform, and you try to converge to this by turning over finite terms of those, then you also get Gibbs phenomena. So yeah, the convergence here is a bit tricky, but anyway, most of the function we touch in the class, they should converge in some sense. Okay. Okay, so any question about the second duality, the derivation, etc.? If not, then let's talk about the application of our discrete time Fourier transform. Okay, and this is the last topic of this chapter, and this is basically similar to chapter 4. So this is an application of why, one of the most important application of why we want to do this for the discrete Fourier transform is that we want to solve those difference equations. Okay, so the linear constant coefficient difference equation look like this. So we talk about this in chapter 2. But anyway, so the constant coefficient because of the ak and the bk are constant, and there is a difference equation because we sum over those y with time shift and x with time shift, and okay, and we're assuming it's a LTI, and so those equations alone is not LTI, and remember it's LTI because we are basically assuming initial rates now. Okay. And anyway, it's LTI. And so how do we solve this is is we use our convolution property. So we think this is LTI, so it will have, so in the frequency domain, we should have this big Y equal to big X times the season function big H. And so we just do Fourier transform on both sides. And the Fourier transform on this side give you the same linear combination. And the big Y and all the time shifts become just is extra factor of e to the minus jk omega. And also the time shift give you this extra e to the jk omega. And so you compare this equation with this equation and you move terms around. So you think YH should be equal to big Y divided by big X. And big Y divided by big X just sum of those terms divided by sum of those terms. So you can just look at the equations and write down the season function directly, just like in a continuous case. But the terms are more annoying now because you have this e to the jk omega instead of, I think it's just j omega before. Okay. And as an example, so we have those difference equation, and assuming initial race, it's LTI, so y of n minus 3 over 4, y of n minus 1 plus 1 over a, y of n minus 2 equal to 2x open. And then big H you can basically just read from the coefficient here, right? So you have this 2 here, then divided by 1, then minus 3 over 4 times is minus 1, so k equal to 1, so you have e to the minus j omega, and the same 1 over 8, and k equal to 2, so e to the minus j2 omega. Okay, so you can read big H directly, and okay, so in big H is easy. Then how to do small h? How to do small h is you apply the inverse Fourier transform from big H to small h. And here we also do so just like chapter 4, we do the partial fraction expansion so that we can plug in the formula to do the inverse Fourier transform, because doing the integration might be hard. And okay, so partial fraction expansion, you factor all the denominator. And so hopefully you are handling good numbers, and here we are giving good numbers, so you factor perfectly into this 1 minus 1 over 2 e to the minus j omega, 1 minus 1 over 4 e to the minus j omega. So you factor those, then you do partial fraction expansion. You say it's a term with 1 minus 1 over 2 and another term with 1 minus 1 over 4, and then you need to solve for this 4 and the minus 2. So that you actually get a 2 here. And anyway, you do partial fraction expansion, and then you see those two terms. The thing we know, because we know this exponential decay thing will give you this 1 over 1 minus a e to the minus j omega. So a equal to 1 over 2 here, and a equal to 1 over 4 here. So you have this exponential decay with 1 over 4 and exponential decay with 1 over, exponential decay with 1 over 2 and exponential decay with 1 over 4. And the other things are just coefficients and unit step. Yeah, so this 4 become 4 and minus 2 minus 2. Okay, just like before. Question about this example? Not? Then let's see another example. Okay, so it's also similar. Yeah, so in this example, we just give you. Okay, so now it's not even difference equation, it's just a LTI system. But very similar. So you say you have a system function that's just this thing, and it's already factorized in the denominator. And let's say we have input signal equal to this exponential decay with 1 over 4, and then we want to ask what's the output signal. So once again, we go to the frequency domain, and this thing we have to see, so we can already write down its spectrum easily. So its spectrum is 1 over 1 minus a e to the minus j omega, with a equal to this 1 over 4 here. And so big Y is big H times big X, so you multiply those together and it's factor all into something. And now this question, this one is a little harder because you have a square term here, okay? Because you have 1/4 here and the same 1/4 here. And now the partial fraction expansion is a little harder because you have a square here, so you will have the square, the same 1/4 square term here, and another 1/4 not square term here, and then 1/2 term here. So now you have the more complicated partial fraction expansion, but anyway, it can still be done, and you have 3 constants you need to solve for them, and then you invert this into, so the single one-way term go to the same exponential decay, and then you have this square term, then you need to use a different formula. So the formula we reviewed in the start of class, and this square give you, so you have a square here, so instead of just 1/4, you have a extra n plus 1 term here. Okay. And so this is a formula, so you have a square here, then you have extra n plus 1 here, and can I click this? No. And the derivation, remember we derived this in this 5.13, where where we say if we want a square here, then you need to get the derivative on the just one-way term, and then you will get extra e to j omega, so you need to deal with the e to where do we do? So okay, so you need to do differentiation, and so differentiation gives you this 1/extra n, and you need to deal with this extra j omega by doing a time shift. So that's why it's n plus 1 here, etc. Okay, so let's go back. Okay, so yeah. So that's how you solve difference equation. You basically look at them and write down big H and do the partial fraction expansion work to then to bring it to small h. And that's what you want. What do you do if you want small h? And if you want say small y, then you multiply big H with big X, etc. Okay. So yeah, so I guess this one can be also viewed as solving difference equation. So this one is saying that you have this difference equation, and if you input is yx is like this, then your output y will be this. And obviously we are doing with initial race condition, so the other LTI. Okay, and summary is not much, doesn't say much. But anyway, summary is that we have a discrete Fourier transform. It's very similar to a continuous time, but now the frequency domain is always periodic with period 2 pi, etc. Okay, so that's it. I think we can stop early today, and on Friday we will probably start the next chapter, and also remember next Friday we will have our midterm 2. And so here, up to here is all the things we want to test on the midterm 2. Okay, so any question? Otherwise, see you on Friday. Okay, yeah. Okay. So, okay. Stop.